Guys, welcome to Sunday Mix Online Tutorials. On today's episode, we'll be discussing on field effect transistors. Welcome back. In the previous video, we discussed on bipolar junction transistors, which are bipolar and field effect transistors are the major type of transistors that we have. So now in this video, we'll be discussing on field effect transistor specifically, and we've established the fact that bipolar junction transistor is a three-terminal device. So also is a field effect transistor. It's also a three-terminal device. But in this case, field effect transistor is a unipolar device. What it means is that it carries a P channel, or it carries an N channel. You can call it an N-type semiconductor, or you call it a P-type semiconductor. Now this depends on only one type of charge. This unipolar field effect transistor depends on just one type of charge, and it's either it carries free electrons or it carries the holes. So now there are basically two types of field effect transistors. The first one is the junction field effect transistor, which is abbreviated as JFET, and the second one is the MOSFET, which is the metal oxide semiconductor or field effect transistor. Now, unlike the bipolar transistors, which are current controlled device, a field effect transistor is a voltage controlled device. What it means is that an input, like when you input voltage, into the transistor, it controls an output current. When you input a voltage, it controls an output current in that device. Now the input impedance is extremely high in a field effect transistor. That is majorly the reason why it is used mostly in electronic devices. That reason being that its reason being of high impedance. It's high impedance, and this high impedance I'm talking about ranges to mega ohms. It ranges to mega ohms. Now the high impedance are the reason why filters are sometimes preferred over bipolar transistors. Now let us discuss on the two types of the field effect transistors, which are the JFET and the MOSFET. We'll be discussing first on the JFET. Now the JFET is represented schematically as this. You have the drain. You have the drain here. You have the source, and you have the gate 1, and you have the gate 2 at that point. So now this is a PNP transistor. So it is an N channel. Now the distance or the space between this drain and the source is called the channel. From this drain to this source, the space between it is called the channel. So when you see this, you call this an N-channeled JFET. If it's a P-channel JFET, it is going to be NPN. Do you understand what I'm saying? So that's how it goes. So now in an N-channel JFET, the majority carrier is free electrons. In this JFET that is drawn here, the majority carrier are the free electrons, and the minority carrier are the holes. But in a P-type JFET, P-channel JFET, the majority carriers are holes, while the minority carriers are the free electrons. Now, this is some schematic. Let me give you some schematic symbols to represent the JFET. You can represent the JFET in this manner. You can call this the drain, call this the source, and the gates. Can represent the JFET in that way. Now you can call this one the N channel transistor. You can the N channel JFET. When you say this is the PNP, This is the N channel transistor. Why the P channel transistor? It is the NPN. So now we've now acquainted ourselves with JFET. So let us see the operation of a JFET in an electronic system. So now let me give you a schematic representation of it. Now let us assume now that the JFET is connected to a battery source. Let us say this is the JFET, and let us use the N-channel JFET. These are the gates, these are the drain, and this is the source. Now, when in a JFET, the current, especially in this system, the current flows this way in an N-channel JFET. The current flows out of the drain, into the source. So now here the amount of current that flows into this system depends on majorly two factors. The amount of current that flows into this circuit depends majorly on two factors. The first factor is the value of the drain source voltage, VDS. The value of the drain source voltage, which is VDS, and the drain source resistance, that is RODS. Those are the two for the current that is flowing into this system. So now that means let us get our hands on the drain current. Let us get ourselves with the formula, acquainted with ourselves with the drain current formula. We say the drain current formula can be presented as ID is equal to IDSS open bracket 1 minus VGS over VGS off. That is the off voltage. So now you say ID, which is current, which is the drain current, is equal to IDSS, which is the current flowing out of the drain, coming out of the source, back to the source, also back to the drain. It's just like it's just looping. So minus 1 minus VGS, which is the voltage gate and the gate source voltage, source voltage. So now let us see an example. Let us see an example to buttress more on this formula that we have been out show that have been established. So now the example says a depletion type MOSFET has the following characteristics. The first one is IDSS equals to 10 milliamp, and the VGS off voltage equals to minus 4 voltage. Now our question is to calculate the drain current for VGS, which is equal to plus 2 volts, VGS, which is equal to minus 2 volts, and VGS equals to 0 volts. So now the solution. What we are looking for is to calculate the drain current, which is this. When we talk about this formula, IDSS open bracket 1 minus VGS over VGS off voltage. So our ID for A is IDSS, which is 10 milliamps, 1 minus VGS. Our first VGS we are given is 2 over VGS off voltage VGS, which is minus 4 volts, all squared. The formula all squared. It was not imputed then, sorry. So now we have ID equals to 10. Then you get your LCM. You get your LCM here. Then when you get your LCM, then you use the 10 to open the bracket. When you've successfully calculated, your ID should be about 22.5 milliamps. That is for the question 1 we're given, and the second part of it, our VGS equals to minus 2 volts. So our ID equals 10 milliamps open bracket 1 minus 2 volts over minus 4 volts. if you solve it correctly, your ID should be equal to 25 milliamps. So on the C part, we say our ID is equal IDSL, which is 10 milliamps, equals 10 milliamps over 1 minus, and our VGS here is 0/4. So our ID is equal to 10 milliamps. So now this formula is only applicable when VDS is equal or greater to VDS pitch. Actually, most of the time you won't find this condition meeting you when you are solving, but just have it in your mind that you use this formula only when the VDS, which is the drain source voltage, is equal or greater than the drain source voltage pitch. So now let us go into the biasing. Let us go into biasing of this FET. Remember in the previous video we discussed on what biasing is and how to bias a transistor. Actually, biasing is just the control of the current, or the control of the voltage in that transistor. So now the way to bias this or the way to control this JFET, the first one we have is the self bias. You can control the current or voltage in this JFET through self biasing method. And when we talk about self biasing method, the voltage of the source, I'll just be dropping the formulas now for you to just use in solving. For the voltage of the source, we have ID RS, so you can get your Bible to write these formulas down. The first one is VS equals to ID RS, VGS equals to minus ID RS, and our RS is equal to minus VGS of voltage over 2 IDSS, and our VD, which is the voltage of the drain, is equal to VDD minus IDRD. We're using this formula mostly when calculating problem involving MOSFET or even JFET system or circuit. So now we've discussed now on JFET. Let us go to the second part of the field effect transistor, which is the MOSFET. Let's go on the MOSFET. Now there are two basic types of MOSFET. We have the enhancement type MOSFET and we have the depletion type MOSFET. Now the key difference between the JFET and the MOSFET is that the gate terminal in a MOSFET is insulated. The gate terminal in a MOSFET is what? Insulated. Let me diagram that so you can see. So now this is the MOSFET. This is the MOSFET. There is going to add a MOSFET is going to be added a substrate. MOSFET is going to be added a substrate. That is, there's going to be added an organic substance, which is a carbohydrate, which is under the carbohydrate family. So you have the NPN. Now this is the substrate. This is the schematic representation of a MOSFET. This is the substrate. Then this is the drain. This is the drain. This is the source. So now this is where the insulated. This is where the semiconductor is applied. On, or the insulator is applied in the MOSFET. Actually, what makes the MOSFET quite more effective than the JFET is that it's just the presence of this insulated material. Just the presence of it, and this insulated material is a silicon dioxide. This insulated material here, which is silicon dioxide, before you get the gate. So it is the gate of the MOSFET is insulated. So this is the gate. So that's the gate there. So that's what just makes the MOSFET quite more effective or quite more useful than the JFET, just because of the insulated gates of the MOSFET. So now we've discussed on that. Now let us discuss on the biasing of this MOSFET. MOSFET can also be biased self. the first way of biasing the MOSFET. Number one, you can bias it self biasing method, and the rest. And the rest we can go. So at this point, I'll be dropping a comprehension so you can get yourself familiar with this topic. And in the next video, we're going to buttress more on some calculations involving MOSFET and JFET. Please do have a wonderful day. Bye bye.